Imagine, just for a second, stepping out onto the surface of a world where the sky has absolutely no sun.
That is quite a bleak picture right out of the gate.
I mean, it really is. No dawn breaking over the horizon, no dusk, not even, familiar constellations of stars, just a permanent, suffocating, freezing darkness.
Right.
And yet, this world isn't just, like, floating aimlessly in the empty voids of deep space. If you were to look up, the only illumination would come from this terrifying, distant halo of violet and X-ray light.
Which is just swirling around a literal hole in the universe.
Exactly, a hole in the universe. And I know this sounds like pure science fiction, but today's deep dive is custom tailored for you if you love those massive mind-bending aha moments.
The kind that force you to completely reevaluate, well, basically the architecture of the cosmos.
Yeah, because our mission today is to completely shatter the traditional definition of a planet. We are pulling our insights from Chapter 7 of the book Planets, The Forges of Black Hole Worlds.
And we're also leaning heavily on some incredibly dense, groundbreaking supercomputer simulations. These were run by astrophysicists Keiichi Wada, Yusuke Tsukamoto, Ichiro Kokubo, and D. Toyuchi.
Right, and it's wild stuff because our entire historical, even scientific framework for what a planet is relies on illumination.
Oh, absolutely. Even the word itself. I mean, it derives from the Greek for wanderer among the stars. We picture a star and then we picture a rock or a gas giant catching that star's light.
I know. Like, think about every exoplanet discovery we've celebrated over the last 30 years.
Yeah.
Whether it's a scorching hot Jupiter hugging its star or, a rocky world bathed in the dim red radiation of a dwarf star, every single one owes its existence, its heat, its very definition to a parent star.
It's this incredibly comforting binary. You have the star that anchors the system and the planets that orbit it.
Right, which makes this specific deep dive so compelling. We're taking that comforting binary, that ancient definition, and completely dismantling it.
We really are. We are looking at worlds that never had a sun to begin with.
But we should probably draw a firm line here early on, right? Because when you say a world without a sun, to people who follow astronomy, the mind naturally jumps to rogue planets.
Oh, sure. And astronomers have found those. I mean, planets that formed in a completely normal sunny solar system, but got gravitationally bullied, essentially.
Like thrown out into the interstellar void by a larger gas giant. A tragic cosmic eviction.
Right. They had a sun and they lost it, but that is absolutely not what we're talking about today.
No, we are talking about a planet. A black hole planet.
It's quite the portmanteau.
Astronomers always manage to come up with these slightly goofy, playful names for the most terrifying phenomena in nature, don't they?
They really do. But the physics behind a planet is, well, it's not goofy at all. These are massive dark worlds that form, live, and potentially die orbiting directly around a supermassive black hole.
And I spent hours poring over these sources, and it just breaks your brain. So we're going to unpack how these worlds are forged in arguably the most violent environments in the universe.
And how they fight to survive their own creation.
Yes. And what this means for the future of our very own Milky Way galaxy.
Well, to really wrap our heads around this, we have to start by zooming way, way out. We have to travel to the only environment capable of building a planet.
The core of a galaxy.
Exactly.
Let's lay the groundwork for you listening, because when most people hear black hole, they think of a dead star, right?
Yeah, a stellar mass black hole, maybe 10 or 20 times the mass of our sun.
Formed when a giant star goes supernova and collapses inward. But that's a pebble compared to what we're dealing with here.
A literal speck of dust in comparison. The planets we are discussing do not form around dead stars. They form around supermassive black holes.
Supermassive. We are talking about singularities with masses that are millions, sometimes billions of times the mass of our sun.
The colossal gravitational anchors sitting at the center of nearly every large galaxy, including our own.
Millions of suns crushed down into a single point. It's a scale that just, it defies human intuition entirely.
It really does. But the black hole itself is just the anchor. To build a planet, we need to focus on the storm swirling around that anchor.
Right, what astronomers call an active galactic nucleus, or an AGN.
An AGN, yes.
Now, to make this accessible, when I first read about AGNs in the sources, my brain immediately went to a cosmic wood chipper. Stuff falls in, gets shredded, and disappears.
I see where you're going with the shredding aspect, but a wood chipper implies you're just dropping things straight down into a set of blades.
Okay, fair.
Gravity doesn't work quite that cleanly. The universe is constantly in motion. Everything is spinning. So when vast clouds of gas, dust, and, the occasional unlucky star begin falling toward a supermassive black hole, they don't plunge straight in.
They get caught in the spin, like a whirlpool.
A whirlpool is much closer. Or think of a ball of pizza dough.
Pizza dough.
Yeah, when you spin the dough in the air, a centrifugal force flattens it out into a wide, thin disk.
Oh, right. Okay.
That is exactly what happens to the matter falling toward the black hole. The conservation of angular momentum forces all that chaotic material into a swirling, flattened structure called an accretion disk.
And the inner region of that accretion disk-like, the part closest to the event horizon, is just pure violence. The text describes it as one of the most extreme environments in all of physics.
Without a doubt.
Because the material closest to the black hole is orbiting at an appreciable fraction of the speed of light, right? And it's rubbing against the material just slightly further out, which is moving a little bit slower.
Exactly. And the sheer friction generated by those different layers of matter grinding against each other is basically incomprehensible. We are talking about temperatures spiking into the millions of degrees.
Millions, not thousands. Millions.
The heat is so intense that matter simply cannot remain intact. Atoms are literally stripped of their electrons.
So everything just becomes a superheated plasma.
Right. And because plasma is electrically charged as it swirls at near light speeds, it generates these colossal twisted magnetic fields.
Which, according to the sources, get wound up so tight by the rotation that they frequently snap.
Yes. Creating literal fountains of magnetic energy and shooting jets of particles perpendicular to the disk out into deep space.
Okay. I have to stop you there because this is where my deep skepticism kicked in while reading the material. I'm putting myself in the shoes of the listener right now.
Sure.
You're telling me a rocky planet forms inside a million-degree plasma blender that shoots out literal death rays.
I know how it sounds.
Because the fundamental prerequisite for planet formation is that rocks and dust have to gently bump into each other and stick. If you toss a rock into a million-degree plasma whirlpool, it doesn't stick to anything. It vaporizes instantly.
Your skepticism is entirely justified. And frankly, it is the exact reason why astrophysicists ignored these environments for decades.
Right.
Nobody looked for planets near an AGN because the inner disk is an absolute destroyer of worlds. It doesn't create, it annihilates. But that assumption relies on a failure of imagination regarding scale.
Meaning, we need to look further out.
Exactly. We have to travel far, far away from that inner superheated zone.
How far are we backing up?
We need to move out to a distance of roughly 1,000 to 1,000,000 times the distance between the Earth and our sun.
Let me put that in perspective for everyone listening. The distance from the Earth to the sun is 1 astronomical unit. Pluto is about 40 astronomical units away.
Right.
You are saying we need to go out to 1,000,000 astronomical units. That means this accretion disk is vastly larger than our entire solar system.
The sheer physical footprint of an AGN disk is staggering. And when you travel that far out to the outer edges of the disk, the environment undergoes a radical transformation.
So you're out of the plasma blender.
You are no longer in the million-degree furnace. In fact, it is chillingly cold out there. The temperatures drop to just tens of degrees above absolute zero.
The ultimate deep freeze. So the center is the most violent furnace imaginable, but the outer rim is just calm and freezing.
And that temperature drop is the magic variable. Because it is so cold out there, matter can finally condense back into solid forms. The plasma cools into gas, and the heavier elements condense into actual physical dust grains.
And the text gets very specific about this dust, doesn't it?
Yeah.
It isn't just generic cosmic fluff. We're talking about silicon, carbon, and iron.
The fundamental building blocks of rocky planets.
So if you're listening, build this map in your head. In the dead center, a supermassive black hole.
Yep.
Surrounding it, a terrifying, glowing, white-hot inner disk of plasma. But millions of miles further out, an incredibly massive, frigid, dark ring floating in space.
A very dark ring.
And the sources emphasize that this outer ring contains thousands of times the mass of our entire solar system, just in raw gas and dust.
It's the ultimate nursery. You have an overabundance of silicon, carbon, and iron, all sitting in a cold, massive ring.
Ironically, it's an environment far richer in the raw materials for planet formation than the standard, quiet little protoplanetary disks that surround newborn stars.
Far richer.
Okay, so we have the ingredients sitting on the counter. The universe has delivered thousands of solar masses of dust. But how does it actually bake into a planet?
Right, because having the dust isn't enough.
Exactly. It has to somehow clump together. And this brings us to the real turning point in the research. The 2019 supercomputer simulations that completely upended our understanding of planetary physics.
Yeah, Wada, Tsukamoto, and Kukubo essentially looked at this cold outer disk and decided to test the impossible. They asked, could this dust actually survive the ambient forces of the disk long enough to clump together and form a cohesive planetary body?
But they couldn't just look through a telescope to find out. They had to build a universe in a box.
That's the beauty of it.
I always find supercomputer astrophysics fascinating because you're literally coding the laws of nature. You plug in the immense gravity of the supermassive black hole, the thermodynamics of the gas, the friction, the fluid dynamics of the accretion disk.
And then you just hit play.
Right. You hit play and watch how the physics engine resolves the chaos.
And when they hit play, the simulation didn't just form planets, it formed them with terrifying efficiency. But to appreciate how shocking their results were, we really need to contrast it with how normal planets form.
So walk us through the standard recipe first, like how did Earth form?
Well, in a standard stellar nebula, the disk of material around a young, normal star-planet formation is an agonizingly slow, gentle process.
Right.
Dust grains drift around in a relative vacuum. Occasionally, they bump into each other. If they hit at just the right speed, static electricity allows them to stick together. They grow from grains to pebbles, from pebbles to boulders.
It's a very delicate dance.
Yeah,
Because if they smash into each other too hard, they just shatter and go back to being dust.
exactly. Astronomers call that the fragmentation barrier.
A fragmentation barrier. So it takes, what, millions of years?
Millions upon millions of years of gentle collisions for these boulders to eventually reach a size where their own localized gravity is strong enough to start actively pulling in more material. Only then do they collapse into proper planetesimals.
Millions of years of static cling, basically. So how does the supermassive black hole change the recipe?
It introduces an overwhelming amount of aerodynamic drag. Remember, this outer AGN disk isn't a vacuum. It is packed with incredibly dense, highly pressurized gas.
So it's less like dust floating in empty space and more like a hurricane.
A hurricane is a perfect way to visualize it. The gas is moving at immense velocities, creating a massive headwind. Instead of dust grains casually drifting and maybe bumping into each other, the high-pressure gas acts as a physical mold.
A mold!
Yeah, it forcefully pushes the dust grains, concentrating them into highly dense, tightly patched layers along the midplane of the disk.
I see. So the gas essentially forces the issue. It completely bypasses that delicate, static cling phase because the pressure is just crushing the dust together.
It acts as a cosmic accelerator. And once these compressed clumps of dust reach a certain critical mass, just a few hundred meters across, they hit a tipping point.
Gravity takes over.
Exactly. Because the surrounding environment is so impossibly dense, the moment they have enough gravity, they start sweeping up the surrounding material at a phenomenal rate.
And the timeline they extracted from the supercomputer data is what really made my jaw drop. We just established that Earth took millions of years to form. The simulation showed that in the AGN disk, fully formed planetary cores can emerge in a few 100,000 years.
An absolute eye blink in cosmic time.
You essentially have a supermassive black hole speedrunning the creation of a world.
It's incredibly fast.
But this brings up a massive lingering question for me. If there is so much material, thousands of solar masses of gas and dust, and the process is so aggressive, why doesn't the black hole just spit out a million massive gas giants?
Right. Why not endless Jupiters?
Exactly. Why doesn't it just make endless Jupiters?
It's a completely logical deduction. You would expect massive gravity and massive gas to equal a massive gas giant. But the fluid dynamics in the simulation showed something highly counterintuitive. They don't typically form Jupiters, they form super-Earths and mini-Neptunes.
Let's define those terms for the listener because they are distinct classes of planets.
Sure. A super-Earth is a rocky terrestrial world that is significantly more massive than Earth, but lighter than our ice giants like Uranus or Neptune. We are looking at rocky spheres between 1 and 10 times the mass of the Earth.
So massive crushing gravity compared to what we are used to.
Yes. And the mini-Neptune designation comes from the atmosphere. Because there is so much ambient hydrogen gas in the accretion disk, as these massive rocky cores form, their gravity pulls in a tremendous amount of that gas.
Oh, so they get enveloped.
Right. You end up with a huge, dense, rocky core wrapped in an incredibly thick, heavy hydrogen envelope.
So if you could somehow parachute down onto a newly forged planet, assuming your ship wasn't instantly crushed by the atmospheric pressure, the view would be, well, let's just say it's not going to make a great postcard.
It is the absolute antithesis of a vacation destination.
Right. Because even though you are out in the frigid, calmer outer edges of the disk, you are still inside a structure that is actively feeding a supermassive black hole.
Exactly.
The sources paint this vivid, hostile picture. The sky above you isn't dark. The inner accretion disk glows fiercely, but it's not a light you can see with your eyes. It glows in X-rays and gamma rays.
The most lethal, high-energy forms of radiation in the known universe.
So these newborn planets are just bathed in invisible, deadly fire. Their surfaces, beneath those crushing hydrogen atmospheres, are absolutely sterile, irradiated wastelands.
Forged in darkness but baked by gamma radiation.
Yeah.
And that leads to a rather grim realization, actually. Simply forming the planet is only half the battle.
Wait, really? What's the other half?
Well, just because the dust managed to overcome the fragmentation barrier and clump together into a super-Earth doesn't mean it gets a happy ending.
Oh, I see. The birth is incredibly violent, but the actual life of a planet is defined by a desperate, frantic struggle against the very disk that gave birth to it.
Exactly. Once a planet is fully formed, it doesn't just sit peacefully in its orbit. It becomes subjected to a terrifying orbital mechanic called migration.
Right, migration.
We talked about that immense gas pressure, the hurricane headwind that forced the dust together. Well, that gas is still there. It doesn't dissipate just because the planet formed.
So the planet has to constantly plow through it. I'm picturing trying to walk waist deep against the current of a really fast-moving river. The water is constantly fighting your forward momentum.
That analogy holds up perfectly under orbital mechanics. The aerodynamic drag of that dense gas physically steals orbital energy from the planet.
And let's break down why that's a death sentence. In orbit, velocity is what keeps you alive. You are constantly falling toward the center of gravity, but if you are moving sideways fast enough, you keep missing the ground.
Right, centrifugal force counters gravity, but if the gas drag is constantly acting as a brake, slowing your sideways velocity down...
Gravity starts winning the tug-of-war.
Exactly, and the result is a decaying orbit. The planet is pulled slowly, but inexorably, inward. It spirals down the gravity well toward the supermassive black hole.
It's essentially trapped on a cosmic conveyor belt leading straight into a furnace.
And this deadly migration plays out over a timeline of a few million years. Now, that specific time frame is critical.
Why is that?
Because a few million years happens to be the typical active lifespan of an active galactic nucleus. A supermassive black hole doesn't feed forever. Eventually, it consumes all the available material in its immediate vicinity, the accretion disk runs out of fuel, and the black hole goes dormant.
So the planet's survival is literally a ticking clock. It's a race against the lifespan of the accretion disk.
A literal race. If the planet is dragged inward too quickly before the AGN shuts off, the consequences are terminal.
Because it hits the inner disk.
Right. As it spirals out of the cold outer disk and crosses the threshold into the violent inner disk, the environment destroys it. The temperature spikes back into the millions of degrees, the hydrogen atmosphere is boiled away instantly, and then the physics of gravity take over.
The tidal forces.
Yes. The gravitational pull on the side of the planet facing the black hole becomes so much stronger than the pull on the far side that the planet is physically stretched.
Spaghettification. The most cartoonish word for the most violent death in the universe. The planet is literally torn into rubble, turned back into dust and plasma.
It becomes just another meal for the singularity that created it, utterly consumed.
But you raised the question of survival earlier. Do any of them make it? The simulations indicate that yes, some do.
They do, yeah. It all comes down to where they formed in the disk and how fast that clock is ticking. If the AGN exhausts its food supply and goes dormant while the planet is still out in the safe zone,
The conveyor belt stops.
the gas dissipates, the aerodynamic drag vanishes, the planet stops losing orbital energy, and its migration halts. It is left parked in a stable orbit.
But the reality of that survival is almost more haunting than being consumed. If the planet wins the race, its prize is to orbit a dark heart for billions of years. Imagine the isolation.
It's profound.
The fierce glowing plasma of the accretion disk is gone. The radiation storms are gone. You just have this massive frozen world sitting in absolute total silence, a ghost ship orbiting an invisible singularity in the center of the galaxy.
The sources actually mentioned that its only source of light, if you can call it that, would be the cosmic microwave background.
The fading, stretched out heat left over from the Big Bang itself. It is a portrait of ultimate cosmic loneliness.
But the research from Toyuchi in 2021 introduces a third fate, and this is the one that really sent me down a rabbit hole.
Oh, the rogue planets.
Exactly. Not all planets die in the singularity, and not all of them end up parked in the dark. Some of them experience a violent eviction.
How does that happen?
Well, this happens because the outer disk is not a clean, orderly place. It isn't just forming one isolated planet. It is a chaotic factory churning out thousands, maybe tens of thousands of these massive super-Earths.
Right, it's a crowded highway.
And as all these massive bodies are migrating inward, fighting the gas drag, their orbits begin to intersect. We get into complex N-body orbital dynamics. If two planets pass incredibly close to one another, or if a planet interacts at just the right angle with the complex gravitational anomalies near the black hole, it can result in a gravitational slingshot.
And wait, we use this exact same physics to explore our own solar system. When NASA launched the Voyager probes, they didn't have rockets big enough to shoot them all the way to Neptune, so they aimed them at Jupiter.
Let Jupiter's massive gravity pull them in, yeah.
And then whipped them around the back, stealing a tiny fraction of Jupiter's orbital energy to violently accelerate the probes outward.
It's the exact same principle, just scaled up by a factor of millions. The gravitational interaction imparts a massive sudden burst of kinetic energy to the planet. It accelerates so violently that it exceeds the escape velocity of the supermassive black hole.
It snaps the gravitational tether.
It is hurled outward, traveling at millions of miles per hour, ejected not just from the accretion disk, but potentially from the galactic center entirely. It becomes a rogue planet, doomed to wander the empty interstellar voids between the stars.
But the text makes a brilliant distinction here. We've found rogue planets before. But a rogue planet is fundamentally different. It carries a fingerprint.
A profound chemical signature, right. A normal rogue planet born around a star has a predictable ratio of elements. But a rogue planet was forged in the extreme, high-pressure, highly enriched environment of an Aegean disk.
So it's made of different stuff.
It would have a radically different core composition, heavily enriched by the specific isotopes and heavy elements concentrated in that violent storm.
It's like a geologist finding a rock in the middle of a calm prairie, but analyzing it and realizing it has the exact chemical signature of a deep-sea hydrothermal vent. You know immediately that it didn't form there. You know it was violently thrown there from somewhere much darker and much more extreme.
Which naturally brings up the most frustrating paradox of this entire field of study.
If the universe is constantly churning out these planets, if it's leaving them parked in the dark or violently slingshotting them out into the galaxy, why is our night sky completely devoid of them? Why haven't we bumped into one?
And this is where theoretical astrophysics hits a brick wall against observational reality.
It always does, doesn't it?
It does. I mean, the physics works, the math is sound, the supercomputer simulations confirm the mechanics. But our current technological ability to actually see them is hopelessly inadequate.
I want to focus on this for you listening, because it's the part of astronomy that can drive you absolutely crazy. We know they should be there, but the sheer agonizing scale of the universe keeps them hidden.
It's vast.
Let's look at the absolute closest possible candidate where we could search for a planet. Sagittarius A, the supermassive black hole sitting at the center of our own Milky Way.
It sounds close because it's in our galaxy, but Sagittarius A is 26,000 light years away from Earth.
26,000 light years.
Yeah.
And we're looking for a rocky sphere that emits no visible light of its own, doesn't reflect the light of a star, and is buried in the most crowded, dust-choked, radiation-flooded region of the galaxy.
The sources do the brutal math on this. Even if you had a planet 10 times the mass of Earth orbiting Sagittarius A, from our vantage point, it would be smaller than a single pixel on our most advanced camera sensors.
Smaller than a pixel.
You are running into the fundamental diffraction limit of light. Even if you built a telescope the size of the entire Earth, you physically could not resolve a direct image of a dark planet at that distance.
So direct imaging is completely off the table. But astronomers are famously stubborn. If we can't see the monster in the dark, we have to look for its footprints. How do we indirectly detect a planet?
Well, there are three primary indirect methods currently being theorized. The first is looking for structural damage in the accretion disk itself.
Looking for the wake of the ship rather than the ship.
A good way to frame it. As a massive planet forms and begins its migration through that dense outer disk, its gravity actively sweeps up gas and dust. In the simulations, this creates a distinct physical structure, a clear-out ring, or a massive spiral gap carved deep into the disk.
Sort of like how the moons of Saturn carve those perfectly clean, empty gaps in Saturn's rings through orbital resonance.
The exact same gravitational mechanism, and we actually have tools to look for this. The text points to the LMA telescope array down in Chile.
Right, Alame.
LMA doesn't look for visible light, it looks for millimeter wave emissions. It essentially looks for the faint thermal glow of cold dust. And LMA has actually imaged these kinds of gaps and asymmetrical ring structures in the accretion disks of a few nearby active galaxies.
Okay, I have to play the skeptic again, because the sources are incredibly careful with their language here. Seeing a gap in the dust doesn't mean you found a planet. The text explicitly states that Occam's razor has to apply.
It absolutely does. While a planet is a thrilling explanation for a gap, it is not the simplest.
Right.
An AGN disk is a fluid, chaotic environment. Those gaps could easily be caused by natural turbulence in the gas or by complex magnetic field instabilities snapping and clearing out pockets of dust. It is a compelling circumstantial clue, but it is far from a smoking gun.
So if looking at the structure of the disk is ambiguous, what's our second option? Are we just hoping one of these things crosses in front of the black hole and blocks the light?
That is method number 2, transit photometry.
Like with exoplanets.
It's the exact same technique we've used to discover thousands of normal exoplanets. We watch a star, and if it dims slightly on a regular periodic schedule, we infer that a planet is passing between the star and our telescope.
But applying that to a supermassive black hole seems wildly optimistic.
It relies on an incredibly lucky cosmic alignment. You need a planet that is migrating inward, and its orbital plane has to be perfectly edge-on from our perspective on Earth. If it crosses in front of that tiny, super hot inner region of the accretion disk, it would block a fraction of the X-ray or optical light.
But here's the problem I see with that. Normal stars are relatively stable. Our sun doesn't just randomly flicker by 20% every Tuesday. So a tiny dimming from a planet is obvious.
Right.
But an AGN is a churning, violent storm of plasma. It is naturally flickering, flaring, and spitting out varying levels of radiation all the time. The background noise must be deafening. How do you find the tiny shadow of a planet in a storm of X-ray flares?
The signal-to-noise ratio is a nightmare. It requires an immense data set to filter out the random noise and find a repeating pattern. The sources place their hope in next-generation technology, specifically the Rubin Observatory's Legacy Survey of Space and Time, or LSST.
I've read about the LSST. It's essentially going to record continuous time-lapse movie of the entire visible night sky.
By capturing the sky every few nights for a decade, it will generate a staggering volume of photometric data. The hope is that through sheer statistical brute force, we might catch the periodic dimming of an AGN that perfectly matches the orbital signature of a planet.
It is a massive roll of the cosmic dice.
Which brings us to the third method, and honestly the one that sounds the most like dark magic to me. Gravitational microlensing.
Pure Einstein. General relativity dictates that mass physically curves the fabric of space-time. If you have a very heavy object like a planet, and it passes directly between our telescope and a more distant background star.
The planet's gravity acts as a physical magnifying glass.
Yes. It bends the light rays coming from the distant star, focusing them toward Earth. To our telescopes, the background star suddenly spikes in brightness for a few days or weeks, and then fades back to normal as the planet moves out of the way.
We use this technique right now to find those rogue planets we talked about earlier, drifting in the empty space between stars. Because they have no light, we just wait for them to magnify a star behind them.
We do. But applying microlensing to find a planet near the galactic center is excruciatingly difficult. The galactic center is not empty space. It is packed with tens of millions of stars, massive dust clouds, and swirling gas.
Ooh, much interference.
Trying to isolate a microlensing event caused by a planet against the chaotic, brilliant, moving backdrop is mathematically possible, but practically agonizing.
It leaves planets, for the current moment, in the realm of brilliant theoretical physics. The sources refer to them as one of the last great uncharted territories in planetary science.
And I think that's a perfect pivot.
Yeah.
Because even if we never build a telescope powerful enough to see one directly, even if they remain a purely mathematical reality, the very fact that they can exist forces us to reckon with some massive philosophical implications. It shatters the very foundation of how we define a world.
It forces the scientific community to ask a deceptively simple question. What actually is a planet?
Let's break down the criteria. The International Astronomical Union has strict rules. First, a world has to undergo core accretion, meaning dust and rocks stick together to form a solid, differentiated body.
Planets do that.
Second, it has to reach hydrostatic equilibrium.
Meaning it has enough mass that its own gravity pulls it into a round spherical shape. Planets easily clear that bar too.
Right. Third, it cannot have enough mass to ignite nuclear fusion in its core. It can't be a star. Planets are massive, but they aren't stars. But here's the sticking point. The traditional definition says a planet must orbit a star.
And a planet never has and never will.
So is it a planet?
For millennia, our human bias has dictated that planets are the children of stars. We literally define them by their subservience to a sun. The math of planets shatters that bias completely. It proves that the mechanisms of planetary accretion, gravity, hydrodynamics are universal.
They're not exclusive to quiet stellar nurseries.
No, not at all.
It is incredibly humbling. It reveals how parochial our view of the cosmos really is. We thought we understood the boundaries of creation, but here is where my jaw genuinely dropped while going through the research. We've established these are dark, freezing, or violently irradiated worlds. But then the text casually introduces the concept of habitability.
The habitability shock. It is the most provocative claim in the entire deep dive.
Now, to be perfectly clear, no one is suggesting you could walk on the surface of a planet and find a forest. The surface is either crushed by a massive hydrogen envelope, sterilized by gamma rays, or frozen near absolute zero. But the text asks us to look at the moons of a planet.
This requires diving into some truly bizarre, almost paradoxical orbital mechanics. Let's imagine a massive planet, say a super Earth, 10 times the mass of our planet, orbiting safely in the cooler outer region of the Aegean disk. Because it is so massive, its gravitational influence is huge.
It can easily capture passing debris or form its own subdisk of material to create moons.
Just like Jupiter and Saturn have dozens of moons in our own system. Precisely. Now, out in the freezing outer disk, there is no stellar radiation to warm those moons. But heat can be generated internally through a process called tidal heating.
I love this concept. Let's explain how gravity creates heat.
You have three massive bodies interacting: the supermassive black hole, the massive planet, and the moon. As the moon orbits the planet, the immense competing gravitational pulls of the black hole and the planet constantly tug at it.
It's like taking a hollow rubber ball and constantly squeezing it and releasing it in your hands. If you do that fast enough, the rubber actually gets warm from the internal friction.
That is exactly what happens to the rock and ice inside the moon. The gravitational tidal forces physically stretch and squeeze the interior of the moon, generating massive amounts of friction. This friction generates heat from the inside out.
We see this exact mechanism in our own solar system. Jupiter's moon Europa or Saturn's moon Enceladus. They are incredibly far from the sun. Their surfaces are solid ice. But because Jupiter and Saturn are constantly squeezing them with gravity, they have enough internal heat to maintain global, deep oceans of liquid water beneath the ice.
But in the case of a planet, the engine driving that tidal heat isn't just a gas giant. It's the interplay with a supermassive black hole. The text posits that a massive planet in the outer disk could absolutely host moons with subsurface or perhaps even surface liquid water oceans.
That's insane to think about.
And they wouldn't just be heated from the inside, they would also receive a diffuse ambient warming glow from the distant thermal radiation of the accretion disk itself.
I want you, listening right now, to just close your eyes and picture that for a second.
Yeah.
An ocean world orbiting a massive dark planet, which is in turn orbiting a supermassive black hole. The sky wouldn't have a sun. It would be a permanent, swirling, diffuse violet glow from the distant plasma disk. There is no day. There is no night.
It is a completely alien, exotic chemistry.
And yet, there is liquid water. And where there is liquid water and an energy source,
Life finds strange paths. That is the exact phrasing utilized by the sources, and it captures the awe of the concept perfectly. If complex chemistry or even biology can take hold in an environment completely decoupled from a star, relying entirely on the gravitational mechanics of a black hole for its energy, well, it completely redefines the parameters of the Drake equation.
it forces us to reconsider where we should be looking for life in the universe.
It's breathtaking, and it leads to a broader synthesis that really changes the narrative of astrophysics. It fundamentally alters how we view black holes.
In popular culture, and frankly in much of observational astronomy, black holes are cast as the ultimate villains. They are the final endpoints of stellar evolution, the cosmic trash cans, the point of no return that consumes matter and lets nothing out.
The ultimate destroyers. But the existence of planets reframes them as the ultimate engines of creation. They aren't just blindly consuming matter, they are processing it. They are taking raw, dead gas and dust, spinning it up in these massive gravitational forges, and churning out brand new, highly complex worlds. It is an endless, breathtaking cycle of consumption and creation operating on a galactic scale.
Which brings us to the final and perhaps most localized revelation of our journey today. Because this isn't just an abstract story about distant, unnamed galaxies. The sources connect this distant theory directly to the future of our own home.
It brings the physics of planets right into our own galactic neighborhood.
Right now, our supermassive black hole, Sagittarius A, is quiet. It is dormant. It isn't actively feeding on massive amounts of gas, so there is no glowing AGN accretion disk, which means, as far as we know, there are no planets actively forming in the center of the Milky Way today.
But the text makes it clear that is a temporary state of affairs.
The timeline is vast. We are talking millions or billions of years from now, but the mechanics of the universe make it inevitable. The Milky Way galaxy is not stationary. We are currently on a direct collision course with our massive neighbor, the Andromeda Galaxy.
A full-scale galactic merger. And when you smash two galaxies together, it's not like cars crashing. The stars themselves rarely hit each other because space is so empty, but the gas clouds.
The gravitational disruption to the gas clouds will be monumental. Giant, tranquil clouds of fresh hydrogen gas and dust that are currently resting quietly in the spiral arms of both galaxies will be violently shaken loose.
They will lose their stable orbits and be funneled directly toward the center of the newly merging galaxy.
Directly toward Sagittarius A, the cosmic whirlpool is going to get flooded with new material.
The dormant black hole will wake up. As millions of solar masses of fresh gas fall into its gravity well, a new, massive accretion disk will form. Sagittarius A will ignite into a brilliant, active galactic nucleus.
The awakening. And as that disk spins up, as the inner regions reach millions of degrees and spit out plasma jets, we know exactly what will happen in the freezing, calm outer edges. The fresh dust will collide. It will be crushed by the immense gas pressure. It will overcome the fragmentation barrier.
New planets will be born, forged in the fires of a galactic collision, right here in the heart of whatever new galaxy we become.
And the way the source material concluded this thought just gave me chills. It asks us to project our minds way, way into the deep future, long after the Andromeda collision has settled, long after the newly awoken AGN has consumed its fuel and shut off again. In the incredibly deep future of the universe, the star formation in our galaxy will eventually slow down.
The existing stars will burn through their nuclear fuel, turn into white dwarfs, and slowly fade out.
The galaxy will go dark.
The theoretical dark age of the universe.
But the planets will remain. Perfect, silent, dark worlds, locked in stable orbits around the invisible heart of our dead galaxy. They will endure long after the very last stars have faded into black.
It's a beautifully melancholy image, a universe entirely stripped of its light, but incredibly not stripped of its planets.
And I wonder, and the text implicitly invites this speculation, if some distant future civilization, surviving somehow by harvesting the last dregs of energy around a black hole in the dark age of the universe, will look toward the galactic center. They won't be looking for light because there won't be any.
No, they'll be looking for gravity.
Exactly.
Yeah.
They will look for that tiny periodic dimming. They will look for the gravitational shadow of a planet to finally observe and prove what we today only dare to simulate in our supercomputers.
A civilization whose entire worldview is shaped by the knowledge that planets are not the children of stars, but the children of the singularity.
Absolutely incredible. Well, I want to thank you for joining us on this deep dive into the darkest, most violent corners of the cosmos. We've taken the very definition of planet, thrown it into a million-degree plasma whirlpool, and watched it get completely reimagined.
It serves as a potent reminder of how much we still have to learn. The universe is consistently more creative, more violent, and more complex than our standard models predict.
I couldn't agree more. But before we sign off, I want to leave you with one final, original thought to mull over. Something that builds entirely on the mechanics we've discussed today, but brings the terror of the AGN right to our own cosmic doorstep. We talked at length about the rogue planets, the worlds that get violently slingshotted out of their galactic centers, hurled across the universe carrying that unique heavy metal chemical signature forged in the extreme fires of the black hole.
The cosmic fingerprint of the singularity.
Right. Well, the universe is vast and time is incredibly deep. Is it possible that one of these rogue planets, wandering the freezing interstellar void for billions of years, eventually crossed paths with a normal young stellar system? Imagine a normal, quiet solar system, forming around a normal star, perhaps even our own solar system, 4.5 billion years ago in its absolute infancy. What if, as our familiar planets were slowly, gently accreting from dust, the immense gravity of our young sun suddenly captured a silent, dark wanderer? A planet forged in the violence of the supermassive black hole, suddenly dropping into our neighborhood, secretly injecting the extreme alien chemistry of the galactic core into an otherwise ordinary family of planets. We look at the planets in our solar system and naturally assume they all share the same simple, sunny origin. But what if one of them is an imposter from the dark? Just something to think about the next time you look up at the night sky.